Hello, EXE 2020. My name is Lei. Today, I'd like to introduce you this exciting research work on behalf of my other two co-authors. We are all from Ryerson University, Canada. As quantum computers are becoming more mainstream and more programmers started writing quantum programs, one question arises: how should a quantum program be debugged? And that is what I will focus on today. First of all, let's see what happens when you run into a bug in a classical program. As one example, we have a simple Python script on the left-hand side. When we run this script, it raises an exception and prints the stack trace as shown on the right-hand side. The stack trace tells you what type of error has occurred, what variable we referenced, and where it is. It helps programmers to trace back the root cause of a bug. But the things are different for quantum programmers. When you work on quantum programs, for example, with Qiskit, a natural question arises: how to debug your quantum program? Furthermore, are existing debugging tactics for classical programs still applicable? Spoiler alert, it is a little bit tricky and challenging to debug a quantum program. Why is that? Let's look at the fundamental differences between a CC and a QC. Allow me to refresh your memory of what is the state of a CC. It is a sequence of zeros and ones. In other words, a register of n bits can only represent one of 2 to the power of n states at a time. On the other hand, a QC contains q bits. Here, we use bracket notation to represent quantum states. A qubit can be captured as superposition of the orthonormal basis states 0 and 1. Here, the coefficient alpha and beta are called amplitude. Now, n qubits can be 2 to the power of n different states in superposition. Now we see the reason why a qubit can be different. In superposition, a qubit can be in multiple states at the same time until a measurement causes it to collapse into one state or another. In other words, a measurement can change the quantum state. But which one will it collapse into? It is random, and it depends on the probability amplitudes. Here, for the famous thought experiment, Schrodinger's cat, what is the chance that the cat can survive? 50%. Those properties make debugging a quantum program more challenging. In such a case, we need to check if the state of a variable is in superposition. There are two scenarios. When the input state is unknown, for example, when it is generated as an output of another quantum program, then we do not have any general solution, and we have to make decisions on a case-by-case basis. But when the input state is known, for example, as you can see from the circuit example on the right, the initial state of a 3-qubit register is known as 010. Then the quantum state can be regenerated using quantum state tomography. Due to the time limit, I have only focused on one concrete example of superposition in this video. In the paper, we also discussed different debugging tactics based on the natures of quantum programs. If you want to read more details, please refer to the proceedings or our preprint online. That concludes my video today. Please email me if you want to discuss anything with us. Thank you for your attention. Enjoy EXE. Cheers.